only study analysis. You will only study analysis. You will only study analysis. I'm just trolling everybody. You can study analysis if you want. If you want to study algebra, that's fine too. But if you study algebra, I have put a curse on you. You will disappear into a puff of smoke the second you open up an algebra text. I'm trolling. Maybe. But on a serious note, I'm going to go talk about spivaks calculus, monk res, and then a secret little book that I have hidden for real analysis. And the reason I want to say this is because I see videos of these people talking about reading specific books and just offering some garbage books, like straight hot doo-doo garbage books. I gotta dispel the rumors. I gotta time out. We can't be doing none of that here. We gotta be doing books that are actually useful, actually helpful, with an in-depth explanation as to why they're helpful, why certain books are better than other books. Now, I'll preface, this entire video with this. Reading books is dependent. It's dependent on a lot of stuff. If you find that certain books are difficult to read, or you think that it's just really boring, or it's very terse, or there's too many problems, or there's too little problems, each one of these issues has its own book. And instead of me saying the opposite, I guess, each book has its own issues. No, each one of these issues has its own book. Meaning if you really like questions and you really like huge amounts of information to learn extremely in depth, a book called Block's Real Analysis is 100% for you. It's an extremely thick book, talks about everything. Questions not that hard, but there's a lot of questions, covers all the theory as well. Excellent for you. If you like a lot of questions, and you really don't want to study too much theory, but you want to really get down to just like getting down and dirty, spivaks calculus is good. The questions are excellent. The theory is okay. It's good. I wouldn't say it's as good as Block's analysis, but it's good. It's sufficient enough. If you're somebody who wants to study a decent amount of theory and have pretty good questions, there's Apostles' Real Analysis. But in the end, you do have to pick a book, and you do have to continue with that book and go ahead with it and learn all the problems, learn all the theorems and everything. So I think it's a good idea to, flex a little bit of the mathematics knowledge that I have and try to really make your brain primed. I'm going to probe your brain a little bit and give you a little bit of an understanding of what each book I'm going to mention is talking about and where it's used and why it's used. So, now when you go and you learn on your own and you want to study on your own, you're going to ask yourself, okay, well, why did I need to know this previous information? Because it shows up later in this other information, right? So like when you study a theorem in real analysis, it's going to show up. If you study a theorem in regular analysis, it's going to show up in real analysis, right? So we're going to really, really give you the feels, the heebie-jeebies for this type of stuff. So starting off, spivaks calculus. Excellent book in my opinion. Amazing book. I love this book, It's my book actually. No one else can have this book except me. And this book, chapters 1 through 4, pretty good. It sets up about functions, about like induction, proof by induction, inequalities a little bit. And it kind of gets you ready to do chapter 5, which is limits, And in limits is an interesting chapter because normally it's talked about with sequences where you take a set of numbers, and you approach one number, Like, for example, let's say I want to take a bunch of these numbers and then I want them to approach 0. Or we know that we see the numbers look like they're approaching 0. So we decide to index all of these numbers. Well, what happens is, I'll pick 0.1, then I'll pick 0.0001, then I'll pick 0.0001, then I'll keep doing that for an infinite amount of numbers. And when I do that, slowly, arbitrarily, you're getting closer and closer to 0. I think one of my friends, or someone that I actually learned from, told me that you could think of it as a really crazy car crash. Because, it's a pretty morbid example, but, sometimes we got to use examples to get a better understanding, consolidate the information a little bit better. You can think of it as a car crash because, the gas goes and you get a little closer, and the gas goes, you go a little closer, and then as you keep getting closer and closer and closer, you don't really want to hit the wall, but it's in front of you, there's nothing you really do. So you start putting less gas and less gas and less gas and less gas and less gas, but infinitesimally you will end up hitting that wall, but of course it'll be very, very small increments that you'll see yourself get closer to. So that's kind of what limits are, in a sense, with respect to sequences. But something interesting that Spivak does is he covers it with functions instead. So as you can see here, an example of a limit is, in x squared times sine 1 over x, right? So as you can see, the limit, if I take x to go to 0, actually approaches 0 in this case, right? In the regular example, sine 1 over x eventually ends up oscillating like crazy, and the behavior around that point that you're going to ends up being just all out of whack. And you kind of notice this about limits, is that it is really trying to explain to you a behavior of a certain set of elements in the case of sequences, or in the case of functions, explaining something about the behavior of the function. It essentially is saying that the behavior of the function behaves nicely. And this is something you'll notice a lot in analysis, period, is that a lot of this stuff is kind of defining what it means for a function to have a certain type of behavior. Later on in topology, it kind of isn't, right? Topology is a lot more abstract, right? Topology is more about like the structures that analysis uses, right? It's like, okay, we have nested interval theorem, we have extreme value theorem, you have intermediate value theorem. Like, how do we define this, right? Because now the question becomes, I want to define it on multiple different dimensions. We don't want to just pick one dimension, we want to pick multiple dimensions. So how do we start discussing this in a general sense? Because this does exist in a general sense. We obviously know this, right? So now what, right? And that's where topology kind of says, hey, we have an abstract version of what you want, my G, don't worry. I got the abstract sauce. And they give it, right? They give it, and you define it through like open sets and different stuff like that. And compactness and completeness, all these definitions kind of show up in topology, and I'll get to that eventually. But yeah, so limits here, it's defined as functions in Spivak instead of sequences, and it makes a lot of sense, right? Like, this obviously approaches 0. But chapter 6 is where you kind of see a little problem here with the way to define limits. Technically, continuity is if you were to just switch it out with the value of the limit of the domain going to that point with the function value of those of those two values, except now you're taking the difference between those two things, right? So you're saying as x approaches a, f of x approaches f of a. And in this example, as you can see here, this example of a sine function, right, that does technically converge, isn't defined at 0. So this isn't actually a continuous function. This is just simply a function that's well behaved at 0, but not necessarily existing at 0, right? And this is where there's a little bit of confusion, because people might be seeing this stuff about the functions approaching a certain limit and unintentionally think that actually implies that the function actually attains a value at that point. So just to make sure people remember that limits don't behave like that. It just behaves as a thing that approaches a certain value. It just has a convergent point. Doesn't mean that it attains this point, right? I could get a sequence of numbers that don't have 0 in it but will approach 0. This being, of course, sequence of numbers 1 over n, such that n is an element of the natural numbers. This sequence of numbers eventually will approach 0 if you let n go to infinity. So yeah, in this case, it's kind of a interesting thing, continuity and limits, and it's the main precipice. It's like the main magnum opus of this entire book is really about limits. There's like maybe 15 pages worth of limits in this book for one chapter. I think it has the most amount of pages for a chapter besides integration. and differentiation. So it is one of the, it probably has the same, if not more, maybe 20 pages, I think. No, I lied, maybe 15 pages. So it's a huge book, and it's a huge lesson, and it's extremely important. And then you get chapter 7 and chapter 8. Chapter 7 is, this stuff is mainly now about like the different theorems of continuity, right? That's defined on like closed intervals, maybe open intervals. And you get stuff like extreme value theorem, intermediate value theorem. In chapter 8 you get nested interval theorem. So what are these theorems? It's just mainly about like, intermediate value theorem just says that if a function is defined on some interval, that there's always going to be an output of this function if the function is continuous, right? So it's like, if you have like f of something here and f of something here, and you have a value in here, and the function is continuous, then this value is equal to some function's value. So it's always going to be defined, like there's going to always be some like curve that you can't like just take your pencil off. It's like it's always going to be a drawable curve basically. And extreme value theorem just says if it's like a closed interval, then you're going to have a maximum and you're going to have a minimum if it's a continuous function, right? So yeah, I mean, a lot of these theorems, as much as it doesn't seem easy maybe because the proofs maybe don't seem easy because I'm explaining it like this, they're very digestible material, right? For the most part, the first 8 chapters are very digestible. All the differentiation chapters are also very digestible as well. I mean, now you actually use the definition of a limit and instead use it as a way of describing the slope over an infinitesimally small range, right? Like now you're taking like, I think there's like this image of like, you take 2 of these points, you create a line, and then you slowly start making these 2 points get to the same point as each other, and you get like your infinitesimal slope basically at that point, which is your derivative. So you see limits are actually being used now, right? And not just in the sense of like a normal function input, but rather like you get to see it in other facets that aren't just a function input. And of course, that's just for chapters 9, chapters 10, chapters 11 as well. Chapter 12, you get to learn about inverse functions. You'll probably be covering a little bit of this like bijective function stuff, roughly in the first 4 chapters. Maybe if you learn it on your own, you get to see that too as well. But, you get to see the derivatives as well of inverse functions. So overall, very intriguing, very important first half, I guess, I would say, of Spivak. And then the second parts are all about integration, right? Chapter 13, 14, 15 is about, chapter 14 is about fundamental theorem of calculus. And then you get chapter 15, which is trigonometric functions. Chapter 16, which is about Newton, stuff about like Newton, physics stuff with Newton. I don't remember 100%, I think it's that. Chapter 17 is about, if I can remember correctly, I think chapters 16 and 17 were about actually something that's completely unrelated to I wouldn't say it's completely unrelated to the rest of the textbook, but it's more just on some other sidetracked thing. And then chapters 18 is about logarithmic functions and exponents, and then chapters 19 is about substitution by parts, substitution, or not substitution by integrating by parts, and use substitution. So Spivak is just really, really good. Sequences and series, though, the main things that I personally think are really fundamental to analysis are not covered earlier on. They're not covered within the first part of analysis, in this book, which I normally see in a lot of courses, that sequences are usually started out first before you kind of cover everything. So that's like the number one kind of issue I have with this, is that sequences should be covered a little bit earlier. But besides that, I think it's normal, right? Series are covered right where they should be, which is next to like Taylor polynomials and stuff like that, which I think should obviously be towards the end of the book after you've finished talking about all this stuff about functions and the derivatives and integrals. And towards the end you get to like radius of convergence, abstracting some of the stuff about series, some other auxiliary stuff, right? Some miscellaneous stuff. Overall, this book has plenty of good questions. Excellent. I would say 9 out of 10 questions pretty much. And I would say the overall theory is maybe a 6 out of 10. But I think this is the best book for an introductory to analysis as you can get. I think that. Maybe other people could say otherwise. This is the first book I actually ever read on pure math, so I'm going to say this right now when I say it. This is my favorite book, all right? No one else can have this book except me. No, I'm just joking. This is an excellent book. Now we move on to after you finish taking, real analysis, or after you finish taking analysis, introductory analysis that is, you get to topology. You might be asking me, well, why the hell does this matter to analysis to begin with? A lot of the fundamentals, right, the fundamental structure of analysis comes from topology. Because you might be asking yourself, like, what is the general case then of a mapping? Like, is there going to always be some sort of like most or the highest value in an abstract setting? Maybe not just in R, right? Maybe I want to define it on another type of space to see if I can still have the extreme value theorem hold or the intermediate value theorem hold. And the answer is yes, right? You could actually have more abstract spaces. You have different spaces that have the exact same property of an extreme value theorem or an intermediate value theorem or a nested interval theorem. So this will eventually teach you that you got to start thinking a little bit more abstractly. I know people say algebra, right? I know I said if you own an algebra book or you open it up, you disappear. But I think after reading so much analysis, I'm immune to it now, But when you read algebra, they tell you, or people tell you, that it's a lot more abstract, way more abstract, they say, right? Way more abstract. And yeah, it is way more abstract, right? It is, truthfully, because you really are building the algebraic structures from the ground up. But I think that really, this is the book that introduces the most abstract thinking, outside of the box thinking. Because algebra, it's like, you're so used to using arithmetic and assumptions on vector spaces and stuff like that. Eventually, then when you read the algebra book, when you learn about group theory, when you learn about ring theory and field theory, you kind of get the vibe of kind of what's going on after group theory, right? I don't know. This is my kind of, this is what I think, right? Like after group theory, you kind of get the vibe a little bit of what's going on. Each algebraic structure moving forward is a little bit more specific with a little bit higher assumptions about what operations have what properties. Right? So, and then from there you can kind of see how much can I get away with these certain algebraic structures that I could still have the same exact definition. I know this is like a general thing for me to say, like that applies to every theorem, but with algebra, like I'm seeing a lot of stuff like, oh, well, you could do splitting fields not just on this specific thing, but you could do it on like this really abstract thing, and this is the theorem for that, So, algebra is very abstract, I would agree, but topology really messes with your brain, right? It really, really messes with your brain. At least that's what I felt like when I first learned topology. After I think maybe after trying to think, it was like maybe the product topology, it like really, really settled into me. This chapter on product topology, it really settled in for me, and I really now got the gist of it. Because it's like you're basically constructing this entire thing from sets. Like this is pretty much just like a nice, elegant way of saying this is a really complicated set theory book, right? Your definition of topology is dependent on how you define a certain set of stuff, right? It's literally a collection of sets with certain properties, right? With certain set operations like union and intersection. So, yeah, it's an excellent book. Your definition of continuity changes as well. I said earlier how it was related to like a function's input and stuff like that. In this book, it's a little bit different. It uses the topological definition, which, talks about open sets and closed sets. So after you define a topology, you actually learn that you can generate topologies with something called a basis, right? To all my fellow lineage people out there, y'all know what a basis is, right? Y'all know what a basis is. So this is kind of the same thing, right? I mean, it's not fully the same thing, but it has an adjacent thing to it, which is, it generates the space. And its definition of an open set is one that contains a basis element. So in the case of, when you look at analysis, you'll read and it'll say, well, a set is open if you can take an open ball, right, inside of the set. And this open ball is actually a basis element, right, of the standard topology. And the standard topology is, of course, a collection of sets of R, right? It's a collection of, you could say, open intervals in R. And this thing is the basis elements that we use, right? And you want to say R of n, and you get a bunch of open balls, pretty much, right, as your basis elements. So, yeah, topology becomes very, very abstract, and it's extremely useful for what I'm about to say soon, very, very soon. And it's very, very cool, right? Algebra gets sprinkled in a little bit towards the end when talking about the fundamental group and some algebraic topology. But the best way to describe topology, man, is that it's a pretty abstract book. It's an excellent book, though. I mean, it's an excellent subject, and I think it's a pretty abstract subject, but it's an excellent book. It comes after analysis because, again, you learn all this stuff here, you learn all the theory here, you got to ask yourself, how can I abstract this away and use other spaces? Because I will explain why it's important for you to abstract all these definitions, right? It's going to be important. It's important because once you learn about topology, the motivation comes in real analysis. Yes, real analysis indeed. Why you might be asking? Because in the beginning of this book is about metric spaces and topological spaces, right? You learn about compactness, you learn about completeness, you learn about open and closed sets, you learn about Berry category theorem, you learn about all this different type of stuff in the first third of this book. Then you get into function spaces. This is where things get a little bit interesting, right? Because you define metric spaces on a metric, right? Like a distance between two elements inside of a set. And what ends up happening is you start looking at function spaces. So you look at the space of functions. So now before you had abstract elements, maybe some elements in R, some numbers or whatever. Now you're looking at functions. And you're looking at the behavior of functions with these topological properties, with these different metric properties, right? So now you're looking at stuff like uniform convergence, pointwise convergence. You're looking at equicontinuity. You're looking at, you're looking mainly at like the sequence of functions, right? You're looking at a sequence of functions now in function space. You're looking at, approximating functions, right? Like, can I use this polynomial to approximate this function for any value that I pick? So, and you learn about different properties, stuff like density and stuff like that. So it becomes a lot more imperative to learn this stuff because a lot of this stuff about function spaces, a lot of the stuff about functions becomes useful in other stuff that you learn in your application engineering classes, such as ODEs and differential equations, right? So when you treat, your algebra equations instead now with a calculus little twist on them in terms of differential equations, now there's a lot harder stuff. Like, the best way to describe it is that like algebra has maybe some straightforward, maybe not 100% straightforward, but like has some straightforward ideas as to like solutions to an equation, right? Like you get a number, there's a solution, and the solution is the number that gives you this value equaling 0. But when it comes to differential equations, the questions become a lot harder because now you're asking what function has this property where if I put this function in here, it gives me this value. And because of that, there's a huge overlap of structure you have to add now to find certain solutions. And if people have been studying ordinary differential equations, you know that like most of them are unsolvable. But for the ones that are solvable, there's a lot of theorems about them. And a lot of these theorems depend on sequences and function sequences. And the solutions are actually just these iterates or these sequence of functions converging to a solution. So this is why it becomes important then now to discuss topology. This is why it becomes important now to discuss the previous information, because those properties allow you to create these theorems for these function spaces to do stuff with these functions in R. So basically what I'm saying is that these topology properties help out with these real analysis properties, which give you stuff for the real analysis to work with now, right? Like now I can make theorems on differential equations because this topology theory lets me do that. It lets me make that assumption that there exists a subsequence that converges, right? That it's like a relatively compact space or something like that, right? So, these, I don't want to say these three books all conjoin together like that, but in a sense they do, right? I mean, like each one, like, you start off with calculus, spivaks calculus, introductory analysis, to dip your toes in, to really understand the theorems, get to know everything really well. Then you learn about a little bit of topology. You don't need to learn from Muncrist. You could still learn from Crowther's real analysis, in my opinion. The first couple of chapters are pretty good. But you learn about topology from this book, and you learn about all these underlying structures, right? Also, not to mention, it's excellent for theorems, and it's also excellent for problems. I would say it's an 8 out of 10 to 7 out of 10 for problems. Not as good as Spivaks Calc, but its theory is like a 9 out of 10, 8 to 9 out of 10 for sure. Overall, solid book. I wouldn't say it's my favorite book. Obviously, calculus isn't. This Spivaks book is my favorite book. And then, we have real analysis co-authors. I'm still going through this book. I'm almost done function spaces. I'm pretty much going to be at Lebesgue and measure theory. So I'll come back to you guys on learning about measure theory and Lebesgue integration. But overall, real analysis, this book, pretty good. I personally don't like it. Contrary to belief, I do think this is an excellent book for reading and learning. I don't like the style of the book, but it was pretty cheap to get your hands on, right? It's an excellent book, honestly, because its theorem is, the questions are embedded to the theorems. So pretty much after you learn a lemma, right after that you have 2 to 3 problems you could work on to exercise the lemma and move on. So it's excellent for learning. Just very boring in my opinion. I just don't think, my style is just not to have like 1,000 questions and 100,000 pages to read. But of course it's useful because for me, I'm basically taking all these assignments, learning them on my own, and then I have no reference book to read from. So I'm literally learning this stuff, like for the assignments and everything, from preemptive knowledge I learned in my ordinary differential equations class, where they like basically went over a bunch of real analysis to come up with the theorems. So having this book is really good because it pretty much just helps me to remember stuff and or new theorems and stuff like that pop up, new lemmas that pop up, so I can do these assignments. So that is the trifecta so far. Of course, again, I said before in a previous video, I'm only going to third year. So this is the conglomerate information of the time that I've spent learning analysis. And I will also be making an algebra video. I've only ever covered Damet and Foot's algebra, but I have Hungersford algebra over here. Went through this a little bit when I first started learning algebra, failed miserably. I read the first couple of pages and I was just like, man, this is just like, some, I don't want to say it's too boring, but I mean, like, part of the book is that it should not be boring to you, but unfortunately, like, if it's just theorem proof, and then I'm just like, man, I can't do this. I gotta have a book that like at least makes things a little bit interesting for me to have the motivation and the dedication to sit down and read, and the discipline. But now that I've finished pretty much Damet and Foot altogether, I think I'm going to probably come back to this and start reading this again. So I think this time it'll be a little bit easier to read. I think I'll probably skip to the parts that I think matter more like modules and stuff like that, and see kind of where I get with this, right? See where I can get with this book. Yeah, excellent book. And of course I got, I said before, if you read an algebra book, you disappear, but unfortunately I got this book as well, Office Hours by a Group Theorist. After covering group theory, again, I bought these books when I didn't know any algebra, and I thought these books were pretty interesting. So now we're gonna, after covering algebra, now we're gonna read and give you my update review on this algebra excerpt. So, yeah. Don't be listening to any BS by people, in my opinion, right? Don't be listening to anyone that's telling you to read, I don't know, like Rudin's analysis on their first try ever learning, right? Like, don't listen to these people. I think a lot of these people are kind of doing this to get less people into mathematics. I don't like that. Like, you're basically stonewalling people and saying, like, dude, like, I studied this when I was a kid, like, you're never gonna succeed, man. Like, you know what I mean? Like, I studied Rudin when I was a little youth. I studied Hungersford algebra when I was in grade 8. Yeah, dude, listen, man. Like, I don't think that you should be telling people that not only that you study that stuff. I think it doesn't really help any conversation if you just have to be like, yo, hold on a minute, G. Yeah, this is something I did. But no, I think I think that, you know, it's not useful to tell people to study hard books, right? That's like my number one pet peeve. Don't be telling people to study hard books. I don't care. Like all these other YouTubers watching my stuff, stop telling people that. Hard books are hard books, and it's good to learn. It's good to learn stuff, but a book should not be difficult. A book should be readable, and the questions should be difficult. It should be the opposite way around, right? It shouldn't be impossible to read a book. It should be a doable thing to read the book, and then it should be difficult to do the questions. So then you learn something. So then you can like sit down and let it consolidate in your brain, because it's not useful for you to just read something, not understand it, and then not understand the questions right afterwards, right? And let's not pretend that like you're the all-knowing freaking, you know, I know everything type of guy, and be like, well, you know, no question and no book is difficult for me. You know, there is always a difficult book. There will always be a difficult book. So that is the dog agreeing with me, actually. So yeah. Anyways, take it easy, everybody.